So we're going to try and present some research done at the TUE with the Spiceball research, which is basically a thing that the TUE organized. And we're students from the True Masters in Cybersecurity. Next slide, please. So hopefully you guys are a little bit aware of what ransomware is, but if not, here's a quick little brief introduction. So ransomware is basically some malicious software that is trying to take the files of a user as a hostage, and then the user can try and get back their files by paying some ransom. Oftentimes this is done through something anonymous such as Bitcoin or stuff like that. And the most common one uses encryption to basically do this. And also it tries to do this as fast as possible, which is kind of a major thing of our solution as well, is that it tries to do this as fast as possible, and it's also kind of the modus operandi of ransomware. Can I get the next slide? So this is basically something that a lot of companies know what this is, a basic computer interface with some Samba shares. And these Samba shares usually hold some sort of information.
Try this.
That doesn't work. So yeah, Samba shares. So a lot of people should know and probably know what these are, and a lot of important information is stored on these. And you expect them to be backed up. But what if that's not the case, or for instance, your backup failed or whatever, something went wrong, like technical issues happen, like you've seen today. And so we thought, well, maybe we can make something that is like a passive listener and could perhaps step in once ransomware attacks these targets, because they are really crucial resources that ransomware could attack, and it's possible that they actually already attack these, because we've seen these cases happening. Can I get the next slide? So this is just a simple example where one host sends some stuff to another host through SMB packages. Nothing really going on here. And now something else is going on. I've marked some packages in red, and these indicate some encryption going on. And still, this is not a big issue because encryption happens, because it's a useful tool to secure some of your files. But what if something like a network where you have a Samba share and a lot of hosts, and some people are sending some encrypted information, and that's all fine and dandy, but what if there's one actor that actually sends a lot of encrypted data? And this could still be fine. But in theory, it could be fine, but in most cases, this is actually a problem for us, mostly because we expect this ransomware to display this sort of behavior of mass encrypting stuff. And so we figured, well, we can make some sort of system that can detect mass encryption. And to do this, we built some exchanges based on the message features that we extract from the SMB data. And then we try and figure out whether these exchanges are encrypted. And if they are, then, well, we can actually say, well, okay, encryption is all fine, but is this, is the behavior that the traffic is displaying, is it actually a user encrypting some stuff? Or is it, for instance, ransomware? So here is our first step. We get some network traffic, we parse it through, we SMB parse it, and we extract some message features, and these features are used to build exchanges, and also to detect encryption. And these exchanges are basically multiple SMB messages that we link up through message identifiers. And here's a really simple one where we create or open a file, and then someone tries to read some stuff, and then it also writes back. This is kind of normal when you are working on some files, but we often notice that ransomware often read a file and then actually use another process to write to the file. And this is harder to link up because it's different processes doing this. And so we had to build some file pattern detection system that actually looked at the file identifiers and looked at the actors that are actually working on the files. And in this way we could build some exchanges that actually just are sort of like a history of all the file manipulations on a single file by a single actor. So now that we have these exchanges, we actually have to try and detect encryption. And we do this using entropy, which can be done on the file data. And what actually entropy means is something that Paulus will explain.
Yeah. Do we have sound? Yes, thanks. Yeah, so on the file system, don't build the exchanges for us, which means that we can see manipulations of the files, and we're looking for encryption. Now, if I have two example files here, the one on the right, or your left, sorry, has a regular pattern, has words, has some structure, and we'll recognize that as a normal file. The one on the right has no such structure and most likely is an encrypted file. We can see this, but in order to build a ransomware detector, we actually have to teach the computer how to see this. And what we use for this is first step is n-grams, which you do in all language processing, is making histograms of all substrings of text. Well, in our case, we're just going to look at 1 grams, which are the bytes represented in a certain piece of text, and then we'll make a histogram for that, so we count the occurrence of each ASCII character. Which we have done for both files presented. The one on the left, the structured file, shows peaks, shows some regular occurrence of characters and some that are less regular. The file on the right has a very flat profile, which means that it's very hard to say which characters are used in this file because they all occur about as frequent. What we can do with this, if you go to the next slide, if we turn this into distribution and actually express the probability, of the occurrence of a certain character. And for encryption, it is important that a cipher text is hard to predict, even if you have a plain text or if you have a key and no plain text. Sorry, can you go? To predict this, and in order to build our encryption detector, we have to turn these distributions into a number that represents something about how easy or hard it is to protect the different bytes in a file. And what we use for this, and Don spoiled it a bit on purpose, is called Shannon entropy. And in the next 5 slides, which will contain a bit of math, I'm going to try to explain how this is computed. For some of you, this might be old hat. For some of you, this might go a little bit fast, but bear with me. Well, we all already have seen probably how to turn a statistical distribution into a single number, because in the 2nd grade of high school we all got the assignment of, hey, if you play the lottery, what is the average result of playing the lottery? So what is your expected value? And in our little example, say if you have a lottery with the odds of 1 in a million of winning the grand prize of $100,000 and a smaller prize that occurs 1 in 1,000 of $100, then computing the average of playing the lottery is a 1 in 1,000 occurrence of the grand prize plus a 1 in 1,000 occurrence of the smaller prize, meaning that if you play in this lottery, you'll get 20 cents for every time you play, which of course usually is not nice if you pay more for the tickets. So these numbers are meaningful, and every one of you of course already has tried once to convert the distribution into such a number. Now if we generalize this, then the mathematical formula for expected value is the sum over all the probabilities of a certain event times a certain value or payoff attached to these events. Now in the case of the distributions we created, in the next slide, we cannot say anything about the certain value of the event, but we can evaluate this in terms of the probability of this event occurring. And as we've seen in the slides earlier, that we're looking for the difference between distributions that have very high peaks and very low peaks and are also very flat. So what we're going to do for this payoff function, we actually want to do something where we calculate 1 over the probability of an event occurring. So if we have a very rare event, a very flat peak, then we're going to attach a high value, which means it's hard to predict. And we have very high peaks, we're going to attach a low value. And for Shannon entropy, we also take the 2 log of this. If you click to the next slide, this has nice properties, such as that the entropy of a binary experiment, say a coin flip, is exactly 1 bit. So the level, the entropy of predicting whether a bit is a 1 or a 0 is 1. And if we fill this into the expected value formula, then we get what is called Shannon entropy. And that's what we're going to use to convert the distribution into a number that is meaningful in terms of encryption. Now, if you got distracted by the math, you can also consider the entropy as the lower bound in the number of yes and no questions you have to ask about a certain experiment in order to guess a result that came from that experiment. In which case, if you have the bit flip, the coin flip again, then it's 1 question you have to ask, whether it's a 1 or a 0, and then you'll know, which is the lower bound for guessing. So we had these distributions from the histograms that we converted. And then on the next slide, the strategy again is we have a text, we turn that in a histogram of the different ASCII characters, have a distribution, use our entropy calculation, and then we have a number that's meaningful, which of course now becomes a filling in exercise. So we have 3 peaks here of a rare occurrence, which we calculate here, then add 2 peaks of more common occurrence, and here we get a number 2.2 something. On the right side we have 7 very small peaks, which we'll also add together according to the formula, and then we get 2 numbers that express what we originally saw. That, in the next slide, sorry. The one on the right is a lower number, or the one on your left is a lower number, and then the one on the right is a higher number, and with some probability an encrypted text. So we now have a tool to say if a certain text is encrypted, and then we need to move on to a behavior analysis of that in order to convert that into an actual detector that helps us to find ransomware. So we need to make a prediction about what kind of entropy values are associated with encryption. Well, we're looking at 1 grams, so we're looking at the ASCII occurrence of ASCII characters in our database. Those are made up of 8 bits to a byte of an ASCII character. So if it is, sorry, can you go back? Yeah. So we expect to find in the theoretical ideal case of proper encryption 8 bits of entropy for this distribution, and of course that the files will use all the available characters about equally as often. So if we're going to the next slide and we're going to build a detector, we're measuring the 1 grams of these files exchanges, and this is going to be a number between 0 and 8 bits of entropy. Then the theoretical model will say that on top, thank you, perfect, we'll have all the encrypted files. Well, real world is slightly more noisy, so we're going to add some bounds to this, and then this is the area where we'll find the encryption. Yeah, so we asked the question, is this actually a good way to predict encryption? So we measure the entropy of a lot of different files, including encrypted files, which is a bit noisy, but it's the column on the left, which indeed adheres to the top of the file. Then you have HTML files, text files, programming files like Python code or C++ code, which is very regular, has words, has patterns, has spaces, uses the readable characters, so it's neatly in the bound of 60% entropy, about 5.5 bits. But then there is this one file type which we found in our experiment that really adheres to the top, even better than our encryption sample, which are PNG files, which are media files. And those files are compressed files. And compressed files, of course, will also have very high entropy, because if there's an easy way to predict what a compressed file looked like, then there's probably a better way to compress it. So we need to find a behavioral method that takes into account entropy, that will indicate whether something is encrypted, but leaves out the false positives. Can you go to the next slide? Of these compressed files. And that is where we started implementing a real detector. And Don's going to tell more about this.
So the detection of encryption is something that we can do, but like we saw, some basic high entropy values aren't going to actually help us. So we know that we need to actually find some sort of increase in entropy in these exchanges that we've already built. And we also know that encryption doesn't really change the size of a file, unlike compression, which is trying to compress the file. And so using these two characteristics, we can actually try and build some sort of detection rule for just encryption. So we did that, and we found some interesting numbers. So here we have some ransomware samples and some true positive rates, which basically mean only encryption. And these numbers aren't too high. Only for Jigsaw we had a really nice true positive rate. The reason that the other ones aren't as high is mostly because there were some files that were too small, and the increase in size was marginally enough so that you would jump over the detection rule threshold that we had. And for instance, this user is actually a really aggressive user that does compression, encryption, some random high entropy stuff, because we scripted him to be really aggressive, because we really wanted to test our detection rule. But the important part here is that we have no false positive rate. And this is because we pretty much excluded anything but encryption or really random stuff. And that's only when you have a file, for instance, that has really low entropy and then actually increases like 30%. And this didn't occur, so that's really nice. So can I get the next slide? Yeah, thank you. So now that we can detect encryption on exchanges, we can actually try and see, well, okay, is this traffic that contains encryption, is it actually ransomware, or is it actually just a user that's performing some encryption? We can do this based on the rate of encryption, which is a fancy way of saying the number of encryptions per second. And then using this, we can actually distinguish between ransomware and just a regular user. So by analyzing the rate of encryption of each of these samples and using some different time frames in which we started with the first encryption that we detect, and then kind of measuring until the time frame, the time frame stops. We can actually see, well, okay, is this ransomware or is this a user, based on the number of alarms that went off because they exceeded the required number of encryptions. So we have another table. What's interesting here is that the user had mostly zeros. This is because the encryptions that the user did were either far apart or just not enough encryptions were performed within the time span. There's only one that actually instance where we can actually say, okay, the user is detected. But if we go to the next slide, we can see, well, the difference is so much that we could do a second filter pass, and then we would still only have ransomware that is being detected by this detection rule. And so we can actually distinguish, as we can show here, between a user, a really aggressive user, and ransomware based on this rate of encryption. So what can you actually use this for? Well, first off, ransomware and intrusion detection system is a really obvious one. But you could also, for instance, block traffic from an infected client, because SMB actually contains the data from where the messages are sent. So you have an IP address that you could block, for instance, if you deem it as ransomware. And another interesting feature that could be implemented is backing up the data that has been recently attacked, because you can store a buffer on our passive listener with the files, because of the SMB data actually going through our passive listener, which also includes the unencrypted data, and then afterwards you get the encrypted data. Can you go back? You can actually back up the data, and then as soon as you block off the infected traffic, you can actually get your files back without any hassle, because you already have the unencrypted files. So yeah, next slide please. Any questions? Also make sure to visit nomoreransom.org and the SpySpot page of the TUE.
Okay. Yeah. I think we managed time pretty well, despite technical issues. We have a question on the first row. Thanks.
How did you implement your passive listener? Passive listener? Did you use Bro EDS or a Python solution?
We used Silent Defense, which is it's being developed by a company that's related to the TUE. I think it's called Security Matters. But it could also be implemented in Bro, because I actually also looked at Bro, but it was kind of handed to us by the guys that also work in the department. So.
There's a question over there.
I see that you guys are having done this in the network level of detection. Have you tried in the host-based level, since the ransomware will basically hit the either maybe end user workstation or server? Do you think this can be done in part of the antivirus or any?
There's already some solutions that do it on the host-based level. The reason why we do it like this is because network drives obviously don't have their own host software. So, and also ransomware could, for instance, interfere with the antivirus solution. And so by doing this, having a passive listener, which can't really be interfered with because you set up your network as such, you actually kind of avoid having to deal with the ransomware attacking your listener. And furthermore, you can actually easily we have a professor at the TUE who is actually like an advocate for just plugging something in and then not looking at it again. And a host-based solution usually needs some maintenance. And you would also have to implement, for instance, for a company with 300 hosts, you would have to deploy it on 300 hosts, while this could serve like a single entity.
However, your point that the mechanics will work on a host-based system are completely correct. That if you find a way to find the exchanges within your host, then our detection rules would also apply to doing it on a single machine to fight the infection there.
Another question: when you compare the between the normal text or statement and the encrypted one, is it going to be any difference if you guys if there is any other languages, any other, let's say, I don't know, Chinese or something that your behavioral?
Probably not, assuming that the Chinese language and character set has structure. What distinguish regular files from the encrypted files is that the encrypted files have bytes distributed uniformly, or at least very close to uniformly, which is something that you're going to see very rarely in normal files, even in different character sets. It might happen particularly for Chinese, where for short messages you will use only a limited set of these characters, and probably will have messages with a lot of unique characters that you might come across some higher entropy files over there. But then it will still hold for a smaller alphabet, so it probably won't go to the full 8 bits of entropy, but if your message is 120 different characters and only 120 different characters long, then you will probably have 7 bits of entropy and not cross a threshold in our system. Move to...
Yeah, thank you. Suppose that the developers of ransomware know about your research. Would it be easy for them to work around this method?
Yeah, actually it's quite easy. I've actually tested this myself because this was for my thesis. And if you actually compress before you encrypt, you totally avoid any detection at all, because the entropy will go up, but the data size difference will then void any detection, because we're trying to avoid detecting compression. And then if you encrypt afterwards, the entropy will not change that much, and the size won't change much either, but you just kind of avoid any detection.
However, if you're going to defend against this, then usually you're going to do things that slow the rate of the ransomware down, which is advantageous in combating it. And our system, in generic sense, is able to adapt to these things. So doing base64 compression, which will make the file longer and lower the entropy, is something that's very well defined if you study the entropy thing. So it is adaptable to the situation. But of course your question applies to any sort of malware versus anti-malware battle, of which we know it is incredibly hard to defend against, and some clever guy has to come around and do one change and he'll change the system. Our advantage probably over some of the things that exist out there is that it is more behavioral based and not based on some blacklist where you just skip out of it. So you really have to find something to either lower the entropy of your encryption, which either means using weak encryption, which is to our advantage, or doing something that is going to make it more noisy or more slow to deploy your ransomware, which probably is going to be a better situation for defending against. But your point stands and applies to most malware research, I think.
Thank you.
So any last question? Then we can go to the next speaker. No questions anymore? Okay, thanks very much, Paulus and Don.